All right, big idea 6, part 2. We are going to do acid-base equilibrium. We have finally made it to the end. So a couple of tools that we're going to use throughout acids and bases. You need to know a bunch of equations. pH equation is negative log of the hydrogen concentration. And that's going to be the same as hydronium. H3O is the same as H2O. I'm sorry, H3O is the same as H+. They're both acid particles. We have a pH and a pOH equals 14. And that comes from the kW of water is 1 times 10 to the negative 14th. So we have our hydrogen concentration times our hydroxide concentration equals 1.0 times 10 to the negative 14th, kW. And then we also need to know in there that kW, when we have conjugates, is also equal to Ka times Kb. So we have an equation set that we're going to continually work with for acids and bases. We need to know how to convert between all of these things. We'll start out with the easiest part first, which is going to be strong acids and bases. Okay, so if we have a strong acid, that's going to be the ones that we had memorized: HCl, HBr, HI, nitric acid, HClO3, HClO4, sulfuric acid, H2SO4, and then HiO4, the periodic acid. What we're looking for there is strong things. It does not mean concentrated. Strong means that the initial concentration is the same as the equilibrium concentration of the acid, meaning it 100% dissociates. There is no equilibrium. It is just the initial is the final. 100% of it goes away. HCl molecules no longer exist. With bases, we have strong hydroxides. So we're going to get the same thing. The initial is the same as equilibrium. You don't really have to worry about equilibrium. You just take the initial. That's how much is in the solution. The hydroxides, however, you have to be a little bit careful because they can be attached to metals that have charges that are not +1. There's a lot of hydroxides that do this. So if we had calcium hydroxide, it dissociates into calcium, but then it dissociates into 2 hydroxide particles. So if we had 2 moles of calcium hydroxide, it does not take 2 moles of acid to neutralize, it takes 4, because there are 4 hydroxides there. Okay, so we need to dissociate that and keep track of the hydroxides themselves. And then if we have those concentrations, we can figure out the pHs. Next section here, we will deal with weak acids. So if we had weak acids all by themselves, and we'll just do acids first. Weak acids only partially dissociate. It's important to note that HF is the only halogen, the only acid with a halogen that's weak. All the other ones are strong. But generically we just say HA, which is H plus, dissociates into H plus and A minus. All the coefficients are 1, so it makes the stoichiometry nice. We can also add the water in there if we wanted to. HA plus H2O, it shows the same thing, makes our hydronium ion plus our anion. And then for these, we have been solving those with ice charts. So let me get in there. So if we had whatever our initial concentration is of the acid, let's say this is 1 molar, we never worry about the water because it's a liquid. We start out with 0 of this, we subtract x, we add x, just like a normal equilibrium problem, we get x, 1.0 minus x. So depending on our Ka expression, we can just say, okay, Ka equals my hydrogen times my anion, my conjugate salt, over Ha. And now there's lots of ways that this problem can go. If we had the Ka, then we simply plug in x times x, so x squared over 1 minus x. You can use your solver, and then you can solve for the hydrogen. Once you solve for x, you know the pH, because negative log of the hydrogen or hydronium is the pH. We could also say things like, oh, the pH is 5. Well, really, what does that tell us? Well, if the pH is 5, then we know x. And we can just plug these things in and get the Ka and use it to identify acids, or just to solve the Ka for itself, or maybe a pKa. So there's ways for them to give us information in these problems to go in and find Ka, or if they gave us Ka, we could solve for x and solve for the hydrogens. So there's our weak acids, just a simple equilibrium. The weak bases, get my pen back out, are not much different. But they have a different balanced equation. So our weak bases, since the hydroxides are the ones we're considering strong, these would be like ammonia. There's a lot of conjugates of acids that are bases, so we need to watch out for those and how to identify conjugates. And then anything, just like the ammonia, anything that's attached to an NH2, instead of having 3 hydrogens, we have 2 hydrogens and then something else. Usually it's a carbon. These are called amines when we get them all connected like that. But those things are bases as well. When we have a weak base, I'm going to use ammonia as the example here. If we look at our balanced equation, NH3 plus water, this is where our base definition comes in really handy, because balanced equations, if you know the definitions, you can write the balanced equations. Acids are hydrogen donors, proton donors. Bases are proton acceptors. They take the protons. So what does the ammonia, this is my base, what does it do? It takes a hydrogen. If you just know that definition, take a hydrogen from whatever you're with, and then you'll figure out the rest of the equation. We'll get NH4 plus, because the hydrogens are positive, and then we're left with OH minus. And this is really the power of why ammonia is a base. It makes this hydroxide ion over here in water. So other than that, we still have an ice chart. So if we had a 1 molar concentration of that, still don't care about the liquid water. 0 of this, minus x, 1.0 minus x, plus x, x, and x. So this is the same thing, except for this one, we get a Kb expression. So the Kb expression is going to be the ammonia, or the ammonium, products or reactants, hydroxide over the NH3 plus. And X in this case is my POH. There's my hydroxide, and we need a POH out of that. So once you get to a POH, you have a Kb, we need a pH. And there are tricky ways to solve for these. You need the Kb because you have a base, but sometimes they don't give you the Kb, sometimes they give you Kas, and you need to go back and say, oh, if that's not the molecule we're talking about, we always know that Ka times Kb is Kw. So we have the equilibrium constant for water. We can convert between Kas and Kbs for conjugates. If they happen to give you the conjugate, then we could solve for those as well. So that should be the easier part of acids and bases if we just had strong things by themselves or weak acids or weak bases by themselves. A little bit more complex, but we're still just building tools. Is going to be mixtures. So mixtures tend to confuse people because you're always looking for a reaction, but mixtures by definition, they're just together. They don't necessarily react. So if you had a mixture, it would be like two acids together or two bases together, but not both. So if you had two acids together, they're not going to react with one another. They're just in the same container. So don't look for a balanced equation. Identify everything and see what you need. If you had two bases together, they're not going to react with one another. They're just in the same container. So different ways we handle mixtures. If we had a mixture of two things that are strong, then both of them are going to contribute here. So I'm just going to handle acids, but bases are the exact same. So if they're both contributing the same amount of hydrogen, or the strong hydrogens rather, we need to add the hydrogens together. Or if they were bases, we would be hydroxides. Add the total together. Total concentration, so total moles over total liters. Usually you have volume changes, so you got to watch out for that. Total moles over total liters, you'll get a new hydrogen concentration and a pH. So it's a mixture of two strong acids or two strong bases. Another way to handle mixtures is if we had one strong, a strong, and a weak. If we had one strong and one weak, in order to get the pH is the strong one only. The weak one does not contribute to the pH. Now there are questions that say, what are the concentrations of these other things in the weak ones? And this is where we have common ion type problems, where this strong hydrogen can come over to this equilibrium of the weak one and suppress that hydrogen. Then you could get the concentration of the anions. And when you have common ions, remember, the initial concentration, the X's don't really matter. When you have common ion concentrations, if you have something to start with, the X's become insignificant for the things that you already have. So it makes the math a little bit easier if you remember how to do the common ions. Another way to handle it is if you had two things that are weak. So these are all our options. Two strong, add them together. Strong and weak, we only want the strong one. If we have two that are weak, we have to do an ice chart. There's no way around it. But one of them is still stronger. So whichever one has a higher Ka, the stronger one, we can't say strong, but the stronger one is going to be the one that affects the pH. The weaker one, same thing, it's going to be suppressed by the stronger one. So the strong one is the only hydrogen that we're concerned with. You don't need to add them together. That gets a little bit tricky. A little bit harder category to identify here is when we get salts. This is where we often see the Ka, Kb conversions. Because if we had, for example, NaF, and we say, hey, what's the pH of a solution that's NaF? Well, we have to look at those two ions separately. Sodium is going to be neutral. It's a spectator. It's the conjugate of NaOH, is how we think about that. Metals are generally going to be the neutral ones. But fluoride is the conjugate of HF. And HF is a weak acid. Therefore, F minus is a weak conjugate base. So this will be, we need to look at this and identify it as a basic solution. This will have a pH that's not 7. So we need to identify that, and then we could do an ice chart for the F minus. So if we knew that the F minus was basic, what will it do? Well, bases take hydrogen, so F minus in water is going to make HF, there's the conjugate, and then the OH minus. So we see that it's making the strong hydroxide. Now we don't usually have Kb values for F minus, so they will give you the Ka for HF, and then you need to calculate the Kb. So watch out for those. When we're identifying conjugates, strong conjugates are neutral. So this is, if we had HCl, or NaCl rather, the Na is neutral, but so's the chlorine. Because HCl is a strong acid, therefore HCl's conjugate, chlorine, will be totally neutral. It's so weak, it's effectively neutral. Strong acids and bases, but those are just the metal ions, have neutral conjugates. They have neutral conjugates. So we have chlorines. It's really just our 7 strong acids. Any nitrates, ClO4, any of these things, if you see strong acid ions, they will be neutral. The strong bases conjugates, those are just going to be our metal ions. So sodium, potassium, lithium, calcium, those things are not going to make, if they're in their salt form with other ions, they're not going to have a pH. And then the last tool for our toolbox is going to be, how do we handle buffers? Buffers are really common ion problems. So there's 2 ways we're going to do this. First, we need to identify a buffer. Buffers are just conjugate pairs. Okay, if we had the acid and its conjugate together in the same solution, they will not react with one another because they just turn into one another. So it's a common ion problem to solve for the hydrogen. So let's just look at an example, that'll be easier. If we had HA, and we always look at the acid version because we want Kas, pKas, pHs. So we always write the acid first, and we look at the acid balanced equation. But this will be a type of common ion problem where, hey, I have 1 molar of my acid, and I have 0.5 molar of my conjugate base. If we went through our whole ice chart here, our hydrogen particle would be unknown. We would say minus x, plus x, plus x, and we could go through this whole process, minus x, x, 0.5 plus x. We could do this. It'd be a lot of work. We could put it all into our calculators if we had them for this portion, no big deal. But common ion problems say we don't have to do this. Common ion says the x's are insignificant. That 1 molar and that 0.5 molar are not going to change. Those are the equilibrium concentrations. Common ions do not change the initial concentrations of things you already have. Now the hydrogen can't stay 0, but there's a quick way to handle that. We just call it X. So there's 2 ways to do this. If we just went right into our equilibrium expression, Ka, you don't need a calculator for this one. This is actually really nice. If you find yourself on a multiple choice, you don't have a calculator, this isn't a solver problem. X times 0.5 over 1, because those 0.5 and 0.1s aren't going to change. And because they don't change and we don't have to worry about that quadratic, this is where we get the Henderson-Hasselbalch equation. So either of these methods, this is where the Henderson-Hasselbalch comes from. pH is pKa, which is negative log of the Ka, plus the log of the acid over the base. I'm sorry, the base over the acid. Wow. It's always products over reactants. Our reactant is always the acid because this is our Ka, pKa equation. our product is always the conjugate base. So products over reactants, just like our K expression, base over acid. That's where I misspoke. So pH equals pK plus log of base over the acid. So these, again, these are our tools that we're going to use. We need to know how to do all of these things before we can solve any neutralization problems. Simple equations: how do you calculate pHs, pOHs, Kas, Kbs, hydrogens, hydroxides? How do we handle them if they're strong, if they're weak? Types of equilibrium problems. If we have mixtures, if we have conjugates all by themselves, or if we have buffers where we have the conjugate pairs both together. And then Henderson-Hasselbalch. All of these things are going to show up in the neutralization reactions that we're about to embark on, and you have to classify which ones do we use in which scenarios. So the rest of this time then, let's just apply these ideas to the neutralization. And then don't forget all of the tools that we have for equilibrium. You really have to know these. You can see all of these scenarios came up. We had strong acid and bases in the excess points. We had weak acids initially or at midpoints, weak bases, same thing. Mixtures, once we get past the equivalence point, we have a strong and weak mixture because the conjugates are there. Salts are all of the anions, and then all those regions we have buffers. When we look at neutralization, the first thing we need to do is identify if we're going to have strong acids or weak acids and bases. So we'll handle each one of those separately. If we had a weak acid and being titrated with a strong base, that'd be a neutralization reaction, or a weak base with a strong acid. We'll never do two weak ones because the math for that can get very, very, very challenging. It doesn't matter which one we're working on, we have a neutralization reaction at first. So our first step, we'll kind of do these together. This is going to be stoichiometry, limiting reactant problems. Okay, our weak acids, generically, we have HA plus our base is going to be hydroxide. It's going to turn into our conjugate and our water, conjugate and water. So this is a stoichiometry reaction. Again, we have three different options. My acid can be limiting, and I have hydroxide in excess. My hydroxide can be limiting, and my acid is in excess. Or they can both be gone at the same time. And depending on the scenarios there, lots of different things can happen. So step one, we have to analyze. Once we get through with the stoichiometry, we have to analyze what's left over. Our first option here, before we do anything at all, we have our acid only. And this is just a simple Ka problem. What is the hydrogen concentration for my weak acid? Okay. As the titration progresses, okay, we'll kind of handle this over here. So step one is right here in the middle. Initial acid by itself. As our titration progresses, my hydroxide will be the limiting reactant, which means my HA is excess. If my HA is excess, I also have my conjugate, and that is a buffer problem. So on our chart here, we have this buffer region in the middle where we have both conjugate pairs. So we have a buffer. And that takes us all the way to the equivalence point. Our third point on that graph is going to be our equivalence point. So we said, okay, only my acid, there's no stoichiometry there because the hydroxide is 0, it hasn't been added yet, and then my hydroxide is limiting, and now we say I have equal amounts of both to get to the equivalence point. At the equivalence point, my acid is going to be 0, my hydroxide is going to be 0. We have the A minus all by itself. And that is a weak base problem. That is the conjugates. We need a KB and for a weak base. So on our graph over here, that's going to be 0.3. At the equivalence point, we have a base. The pH is above 7. And these are really easy to identify kind of how the graph fits with that. Our fourth point is now the acid is limiting and we have excess hydroxide. And anything past the equivalence point is going to be our region 4, and that is just a strong base problem. There is a weak base as well. That is our mixture of bases, but the strong base is going to give us my POH, and we can get our pH. So we have to identify all those regions. Initially, we only have the acid. We have this buffer zone, and don't forget at the midpoint when half the acid has been neutralized, there is that special pH equals pKa right in the very, very, very middle, wherever that is. Half the acid has been neutralized, we get that. It buffers all the way to the equivalence point. The equivalence point, we have the conjugate pair only, and then the hydroxide is in excess, and it's just a POH problem. So that takes us through a weak acid titration. Okay, didn't mean to make the text smaller there. And if we do that for our weak base as well, we can go through the same process. So our weak base, we have our base, and then we're going to add a strong acid to it, and we make a conjugate. Now, initially, we kind of go through the same stoichiometry, the BCA charts, limiting reactants, whatever. Initially, we don't do any of that. So the very, very first point on there that we need to realize, we only have the A minus. That equation up there doesn't exist. It's just a weak base problem. Weak bases plus water make hydroxides and conjugates. We need a KB. This is a weak base. But once we add the acid to the titration, the acid is going to be limiting. We have excess A minus. Okay, we will have, and we made its conjugate. So we make the HA. So on our graph, we can see how this plays out again. Initially, we have the weak base by itself, and then we have a buffer problem. All in this region, there's a midpoint where the pH is still the pKa. Watch your Kas and Kbs there. If you're setting up the base problem, usually you're working with a Kb, so you'd need a Ka in order to make that shortcut work. And you get the buffer all the way until the equivalence point. So at the equivalence point, both the acid and the base titrants are gone. We have HA only because my base is 0, my acid is 0, but we made some HA. So we have HA only. My equivalence point should be below 7. And this is just a Ka weak acid problem. And then anything past that, we have a strong acid all by itself. We have excess H+, all the way past that. So we see how this graph, the titrations represent limiting reactant problems. Initially, I have a weak base. Then I have a conjugate pair buffer. All the acid is limiting reactant. And then the acid and base are totally equal, but I have the conjugate all by itself. We've exceeded the buffering capacity. We have a weak acid problem. And then I keep adding strong acid. I still have the weak acid, but the strong acid determines the pH. We have a mixture of acids. The strong acid wins, and we can determine what the pH is past that. So it's a really intricate calculations and analysis of stoichiometry, balanced equations. There's volume changes, so you constantly have to watch out for what your volumes are, and this is really going to mess up. Well, it looks like there's a bunch of layers here locked together, so we're just going to leave it like that because we're done anyway. But that's the weak base titration, weak acid titrations. So actually first let's handle if we had a strong acid and a strong base. To do that, our net ionic equation is always going to be the hydrogen and the hydroxide turning into H2O. And this is a stoichiometry reaction. This is limiting reactants. We always do that first when we have neutralization. So it's not really an ice chart because we don't have an equilibrium constant. It is a stoichiometry chart, before, change, and after. Now one of these is going to go to 0. Whatever we have, we're going to have some amount of hydrogen, some amount of hydroxide. It's a 1-to-1 ratio, and we've got a couple of options. Either the hydrogen is excess and the hydroxide is 0. The hydrogen goes to 0 and the hydroxide is in excess, or they're both gone at the same time and we only have water, and the pH of water is 7. So this is a very simple limiting reactant problem, and anytime we have a neutralization reaction with an acid and a base being mixed together, they're not conjugate pairs, we have a stoichiometry problem first. There are volume changes, so you often need to work in moles and account for the volume changes for everything when you're all done. It gets much more difficult when we go into weak acids and bases.